Welcome to day 5 of Master AI in 30 days. We've covered mathematical foundations, machine learning essentials, and deep learning fundamentals. Today, we're diving into natural language processing, the technology enabling computers to understand, interpret, and generate human language. NLP is everywhere in modern life. When you ask Siri a question, use Google Translate, get autocomplete suggestions while typing, or chat with ChatGPT. That's NLP at work. It's one of the most impactful applications of AI, fundamentally changing how humans interact with computers. Today, you'll understand how computers represent text mathematically through tokenization and embeddings. You'll learn how language models predict the next word and why this simple task unlocks powerful capabilities. You'll master the transformer architecture and its revolutionary attention mechanism. You'll explore BERT and GPT, understanding their differences and use cases, and you'll gain insights into modern large language models that are transforming AI. By the end of today, you'll understand the technology powering ChatGPT, translation systems, search engines, and text AI. You'll grasp not just what these systems can do, but the principles behind how they work. Let's explore the fascinating world of language AI. Here's what we'll master today: the core concepts that power modern NLP systems. First, we'll understand how text is processed and represented. Computers work with numbers, not words. Tokenization breaks text into units, and embeddings convert these units into vectors that capture meaning. This mathematical representation enables all subsequent processing. Second, we'll explore word embeddings in depth. Words with similar meanings should have similar vector representations. We'll see how embeddings capture semantic relationships. King minus man plus woman approximately equals queen. This isn't magic, it's learned patterns from massive text data. Third, we'll understand language modeling, predicting the next word given previous context. This deceptively simple task is the foundation of modern NLP. A model that's good at next word prediction implicitly learns grammar, facts, reasoning, and world knowledge. We'll see how this one task enables diverse applications. Fourth, we'll take a deep dive into the transformer architecture. The attention mechanism was a breakthrough that revolutionized NLP and beyond. We'll understand self-attention, multi-head attention, and how transformers process sequences in parallel rather than sequentially like RNNs. Finally, we'll compare BERT and GPT, two famous transformer-based architectures with different strengths. BERT excels at understanding tasks like classification and question answering. GPT excels at generation tasks like writing and summarization. Understanding their differences helps you choose the right tool for your task. After today, you'll understand the architectures behind ChatGPT, BERT, and modern language AI. Before we can process language with neural networks, we must convert text into numbers. Tokenization is the first critical step. Tokenization breaks text into discrete units called tokens. The simplest approach is word-level tokenization, split on whitespace and punctuation. The CatSat becomes 3 tokens. This is intuitive but has problems. First, the vocabulary becomes huge. English has hundreds of thousands of words. Second, rare words and misspellings become unknown tokens, losing information. Third, morphological relationships are lost. Run, running, ran are completely separate. Subword tokenization solves these issues. Algorithms like byte pair, encoding, BPE, and word piece learn to split words into common subunits. Running might become. This reduces vocabulary size dramatically. Maybe 30,000 subword tokens cover most text. Rare words are composed from subwords rather than marked as unknown. Morphological relationships are partially preserved through shared subwords. Character-level tokenization is the extreme. Each character is a token. The vocabulary is tiny, 26 letters plus punctuation, and no word is unknown. But sequences become very long, making it harder for models to capture patterns. The choice of tokenization impacts everything downstream. Modern systems like GPT use BPE with vocabularies around 50,000 tokens. This balances vocabulary size, sequence length, and coverage. Tokenization might seem like a mundane pre-processing step, but it's foundational. Poor tokenization means the model sees a distorted view of language, limiting performance regardless of architecture sophistication. Word embeddings are one of the most elegant ideas in NLP. They represent words as dense vectors in a continuous space where semantic relationships become geometric relationships. Imagine a 300-dimensional space. Each word is a point in this space. Words with similar meanings cluster together. dog, puppy, canine are near each other. King, queen, prince, monarch form another cluster. Run, walk, sprint, jog are grouped. The geometry of this space captures meaning. Here's what makes embeddings powerful. Semantic relationships become vector arithmetic. The famous example, king, man, plus woman, queen. This works because embeddings capture the abstract relationship male to female royalty. Similarly, Paris, France plus Italy approximately equals Rome captures capital of country relationships. These patterns weren't explicitly programmed. They emerge from learning on massive text data. How are embeddings learned? Algorithms like Word2Vec train on the distributional hypothesis. Words that appear in similar contexts have similar meanings. If dog and canine both appear near words like bark, pet, walk, they should have similar vectors. The model learns vectors that make context prediction accurate. Embeddings revolutionized NLP. Before embeddings, words were one-hot vectors, binary vectors where only one position is one. These captured no semantic relationships and were incredibly high-dimensional. Embeddings are dense, typically 100-300 dimensions, capture meaning, and enable transfer learning. Pre-trained embeddings like Word2Vec and Glove became standard, providing rich word representations to downstream tasks. Language modeling seems simple. Given previous words, predict the next word. But this deceptively simple task is incredibly powerful and forms the foundation of modern NLP. Consider the sentence. The cat sat on the Eugene house. A good language model assigns high probability to words like mat, chair, floor, and low probability to sky, ocean, equation. To do this well, the model must understand grammar, what parts of speech fit, semantics, what makes sense, and world knowledge. Cats typically sit on surfaces. Mathematically, we're modeling P, word N, E, word 1, word N 1, the probability of the next word given all previous words. For the sentence, the cat sat on the mat, we want P cat, the, XP sat, the cat, times P on, the cat sat times P, the cat sat on, times P mat, the cat sat on, the. A good language model makes this product high for natural sentences and low for ungrammatical or nonsensical ones. Why is language modeling so important? First, a model that predicts well implicitly learns linguistic structure. To predict well, it must learn grammar rules, semantic relationships, factual knowledge. Second, language modeling enables generation. Sample from the predicted distribution repeatedly, and you generate text. Third, it provides a pre-training objective. Train a large model on language modeling using massive unlabeled text, then fine-tune on specific tasks. Modern large language models like GPT are essentially sophisticated next word predictors. Their remarkable capabilities, writing, reasoning, coding, emerge from doing this one task extremely well at massive scale. The transformer architecture introduced in 2017 revolutionized NLP and became the foundation for modern large language models. RNNs process sequences step by step, maintaining a hidden state. This is inherently sequential. You can't process word 10 until you've processed words 1 to 9. This limits parallelization and makes it hard to capture very long-range dependencies. Transformers solve both problems with the attention mechanism. Transformers process the entire sequence at once. All tokens are processed in parallel. There's no sequential bottleneck. This enables much more efficient training on modern hardware like GPUs and TPUs. The attention mechanism allows each token to directly attend to any other token regardless of distance. Information can flow across the sequence without passing through intermediate states. The original transformer has an encoder-decoder structure. The encoder processes the input sequence and the decoder generates the output sequence. Each consists of stacked layers with two main components, multi-head self-attention and feed-forward networks. Residual connections and layer normalization stabilize training. Self-attention is the key innovation. For each token, it computes attention scores with all other tokens, determining which tokens are relevant for processing this token. Then it combines information from relevant tokens using these scores. This happens for all tokens simultaneously. Multiple attention heads learn different types of relationships. Transformers became the dominant architecture in NLP. BERT uses only the encoder. GPT uses only the decoder. T5 and BERT use the full encoder-decoder. The attention mechanism is so powerful it's expanding beyond NLP to vision, audio, and multimodal models. Self-attention is the mechanism that makes transformers powerful. Let me break down how it works. For each token, we create three vectors: query, key, and value. These come from learned linear transformations of the token's embedding. Think of it like a database. Queries search for relevant information, keys determine what each token contains, and values are the actual information retrieved. To compute attention for a token, we take its query and compute similarity scores with all keys. This tells us how relevant each other token is. We use dot product, query, key. The scores are scaled by decay, square root of dimension, to prevent very large values, then passed through softmax to get probabilities summing to 1. These attention weights determine how much each token contributes to the output. We take a weighted sum of all value vectors using attention weights. The result is a new representation for this token that incorporates relevant context from the entire sequence. The formula attention QKV was softmax QKT DKV. QKT is matrix multiplication giving all pairwise scores. Softmax converts to probabilities. Multiplication by V produces weighted combinations. Multi-head attention runs this process multiple times in parallel with different learned transformations. Maybe head 1 learns syntactic relationships, head 2 learns semantic relationships, head 3 learns coreference, and so on. Outputs are concatenated and transformed. Multiple heads allow the model to attend to different aspects of the input simultaneously. This mechanism allows direct connections between any two tokens, enabling long-range dependencies without sequential processing. Self-attention has a subtle problem. It's permutation invariant. If you shuffle the tokens, attention produces the same result. But language depends critically on word order. Dog bites man and man bites dog have very different meanings despite using the same words. Transformers solve this with positional encodings, vectors added to token embeddings that encode position information. For position P and dimension I, the original paper uses PEP 2I, Detour Sin P 10,000 2ID, and PEP 2I per 1, Shirai 2I squares P 10,000 2ID. These sine and cosine functions of different frequencies create unique positional signatures. Why this particular encoding? Several nice properties. It's deterministic and doesn't require learning. The function can extrapolate to sequence lengths longer than seen during training. The dot product between positional encodings of different positions reflects their relative distance. Close positions have similar encodings. Alternative approaches exist. Some models learn positional embeddings, treating position like a token with learned vectors. Others use relative positional encodings that directly model the distance between token pairs. Recent work shows that models can sometimes learn position implicitly from data patterns, but explicit positional encoding remains standard and works well. The key insight: attention provides content-based routing, what relates to what, and positional encoding provides sequential structure, in what order. Together, they give transformers both the parallel efficiency of attention and the sequential awareness needed for language. BERT, bidirectional encoder representations from transformers, was a breakthrough in 2018 that showed the power of pre-training and fine-tuning for NLP. BERT uses only the transformer encoder, stacked layers of self-attention and feed-forward networks. Unlike GPT, which processes left to right, BERT processes bidirectionally. Each token can attend to both previous and future tokens. This bidirectional context provides richer representations for understanding tasks. BERT's pre-training uses two objectives. First, masked language modeling. Randomly mask 15% of tokens and train the model to predict them using bidirectional context. For the cat on the mat, BERT must predict sat, using context from both sides. Second, next sentence prediction. Given two sentences, predict if the second follows the first. This teaches relationships between sentences. After pre-training on massive text data, Wikipedia plus book corpus, BERT is fine-tuned for specific tasks. For classification, add a classifier on top of the token representation. For question answering, predict start and end positions of answers. For named entity recognition, classify each token. Fine-tuning is fast and data efficient because BERT already learned rich language representations. BERT excels at understanding tasks that require comprehending input but not generating text. question answering, sentiment analysis, textual entailment, named entity recognition, BERT achieves strong results with relatively little fine-tuning data. Its bidirectional context is perfect for these tasks. Variants like Roberta, Albert, and Deberta improved on BERT's design, but the core idea, bidirectional pre-training for understanding, remains influential. GPT, Generative Pre-trained Transformer, takes a different architectural approach than BERT, optimized for generation rather than understanding. GPT uses only the transformer decoder. Unlike BERT's bidirectional attention, GPT uses causal, masked attention. Each token can only attend to previous tokens, not future ones. This is necessary for generation. When predicting the next word, you can't look ahead to future words that don't exist yet. GPT's pre-training is standard auto-regressive language modeling. Predict the next token given previous tokens. This is simpler than BERT's masked language modeling. No special tokens, just straightforward left to right prediction. The simplicity is elegant and effective. GPT-1 showed that this approach works well with fine-tuning. GPT-2 demonstrated that larger models are better and introduced few-shot learning. GPT-3, 175 billion parameters, showed that sufficiently large models can perform tasks through in-context learning. Give examples in the prompt, and the model adapts without parameter updates. GPT-4 further scaled capabilities. GPT excels at generation tasks, writing, summarization, translation, code generation. The autoregressive structure is naturally suited for producing coherent text. It can also handle understanding tasks through clever prompting, though BERT-style encoders may be more parameter efficient for pure understanding. The GPT series demonstrated that scaling up decoder-only models with simple language modeling objectives yields increasingly capable systems. This insight drove the development of modern large language models. Understanding the differences between BERT and GPT helps you choose the right tool for your task. Architecture. BERT is an encoder. Bidirectional attention processes the full input to create context-rich representations. GPT is a decoder. Causal attention processes left to right for autoregressive generation. This fundamental difference drives their strengths. Pre-training, BERT uses masked language modeling with bidirectional context. GPT uses standard language modeling with only previous context. BERT sees more context during training, but GPT's objective aligns naturally with generation. Use cases, BERT excels when you need to understand and classify inputs. Sentiment analysis, spam detection, named entity recognition, question answering, textual entailment, tasks where you process fixed inputs and produce labels or extractions. GPT excels when you need to generate text, writing, summarization, translation, code generation, dialogue, tasks where you produce variable length outputs. Adaptation, BERT typically requires fine-tuning, updating parameters on task-specific data. This is effective but requires labeled data for each task. GPT, especially large versions like GPT-3, can adapt through prompting. Provide examples or instructions in the prompt, and the model adapts its behavior without parameter updates. This is incredibly flexible. In practice, the line blurs. GPT can handle understanding tasks through prompting. BERT-style models can be adapted for generation with encoder-decoder architectures. Modern systems often combine both approaches, but the core insight remains: bidirectional encoders for understanding, autoregressive decoders for generation. One of the beautiful aspects of attention mechanisms is that we can visualize what models learn by examining attention weights. Attention weights show how much each token attends to others. For the sentence, "The cat sat on the mat," we can visualize which words the model focuses on when processing each word. Often we find interpretable patterns. The word sat might attend strongly to cat, its subject, and on, its preposition. The word mat might attend to the, its determiner, and on, indicating location. Different attention heads learn to capture different linguistic phenomena. Some heads specialize in syntactic relationships, tracking subject-verb agreement, modifier-noun connections, dependency structure. Other heads capture semantic relationships, attending to related concepts regardless of syntax. Yet others track coreference, identifying when pronouns refer to previous nouns. Researchers have visualized attention in models like BERT and GPT, revealing fascinating patterns. Some heads act like syntax parsers, some track long-range dependencies, some focus on the first or last tokens. The model doesn't explicitly learn these roles. They emerge from training on language modeling. This interpretability is valuable. When a model makes a mistake, examining attention can reveal why. Maybe it attended to the wrong context. Maybe a crucial relationship wasn't captured. Attention visualization isn't perfect for interpreting models. Attention weights don't fully explain model decisions, but they provide useful insights into what information flows where. Understanding what models learn helps us improve architectures, diagnose failures, and build more capable systems. Large language models, LLMs, like GPT-3, GPT-4, PLM, and LLaMA represent the current frontier of NLP. Their scale brings qualitative changes in capabilities. Scale matters. GPT-2 had 1.5 billion parameters. GPT-3 has 175 billion. GPT-4's size isn't public but is larger. Palm has 540 billion parameters. As models scale, new capabilities emerge that weren't present in smaller versions. Few-shot learning, complex reasoning, code generation, mathematical problem solving, these emerge gradually as scale increases. In-context learning is a key capability. Provide examples or instructions in the prompt, and the model adapts its behavior without updating weights. Translate English to French. Sea otter equals loutre de mer, peppermint equals menthe poivrée, plush giraffe equals. The model learns the pattern from examples and continues correctly. This makes LLMs incredibly flexible. But LLMs have important limitations. Hallucinations. They confidently generate plausible sounding but false information. Biases. They reflect biases present in training data, which can be problematic. Reasoning limitations. While they handle many reasoning tasks, they struggle with multi-step logical reasoning, mathematical proofs, and scenarios requiring true understanding versus pattern matching. Context length. Even with extended context, there are limits to how much information they can process. Current research addresses these issues through reinforcement learning from human feedback, RLHF, retrieval augmented generation, adding external knowledge, chain of thought prompting, encouraging step-by-step reasoning, and architectural innovations. The field is rapidly evolving. Large language models, LLMs like GPT-3, GPT-4, PALM, and LLaMA, represent the current frontier of NLP. Their scale brings qualitative changes in capabilities. Scale matters. GPT-2 had 1.5 billion parameters. GPT-3 has 175 billion. GPT-4 size isn't public but is larger. Palm has 540 billion parameters. As models scale, new capabilities emerge that weren't present in smaller versions. Few-shot learning, complex reasoning, code generation, mathematical problem solving, these emerge gradually as scale increases. In-context learning is a key capability. Provide examples or instructions in the prompt, and the model adapts its behavior without updating weights. Translate English to French, sea otter and loutre de mer, peppermint and menthe poivrée, plush giraffe. The model learns the pattern from examples and continues correctly. This makes LLMs incredibly flexible, but LLMs have important limitations. Hallucinations. They confidently generate plausible sounding but false information. Biases. They reflect biases present in training data, which can be problematic. Reasoning limitations. While they handle many reasoning tasks, they struggle with multi-step logical reasoning, mathematical proofs, and scenarios requiring true understanding versus pattern matching. Context length. Even with extended context, there are limits to how much information they can process. Current research addresses these issues through reinforcement learning from human feedback, RLHF, retrieval augmented generation, adding external knowledge, chain of thought prompting, encouraging step-by-step reasoning, and architectural innovations. The field is rapidly evolving. NLP powers a vast array of practical applications, transforming how we interact with information and technology. Text classification assigns categories to text. Sentiment analysis determines if product reviews are positive or negative, helping businesses understand customer opinions. Spam detection identifies unwanted emails. Content moderation flags inappropriate posts on social media. Topic classification routes support tickets to appropriate departments. These tasks use BERT style models trained on labeled examples. Information extraction pulls structured information from unstructured text. Named entity recognition identifies people, places, organizations, dates. Relationship extraction finds connections between entities. Key phrase extraction highlights important concepts. These enable knowledge-based construction, semantic search, and automated summarization. Text generation produces new text. Summarization condenses long documents to key points. Machine translation converts between languages. Dialogue systems power chatbots and virtual assistants. Content generation assists writing. GPT-style models excel at these tasks, producing fluent and contextually appropriate text. Question answering systems provide direct answers to questions. Search engines show relevant information. Virtual assistants like Siri answer factual queries. Customer service bots handle common questions. Reading comprehension systems extract answers from documents. These combine retrieval, finding relevant information, with generation, formulating answers. NLP is foundational to modern information technology. It makes vast amounts of text searchable, understandable, and generatable. As models improve, applications become more capable, enabling interactions with technology that feel increasingly natural and human-like. Tomorrow is day 6, Computer Vision Fundamentals. We're diving deep into how computers see and understand visual information. We'll start with image processing basics, how images are represented digitally, fundamental operations like filtering and edge detection, and classical feature extraction techniques. This foundation helps you understand what problems deep learning solved. We'll explore advanced CNN architectures that push the boundaries of image recognition. ResNet introduced skip connections enabling very deep networks. Inception used multi-scale processing with parallel convolution paths. EfficientNet optimized depth, width, and resolution scaling. Understanding these architectures reveals design principles for visual models. We'll tackle object detection, not just classifying images, but localizing and identifying multiple objects within them. We'll study YOLO, you only look once, RCNN family, and modern approaches. Object detection enables autonomous vehicles, surveillance systems, and countless applications. We'll cover image segmentation, labeling every pixel with its category. Semantic segmentation classifies pixels. Instance segmentation separates individual objects. Panoptic segmentation combines both. These techniques power medical imaging, satellite analysis, and augmented reality. Finally, we'll explore vision transformers, applying attention mechanisms to images. VIT challenged the dominance of CNNs, showing transformers work well beyond NLP. We'll also touch on multimodal models like CLIP that connect vision and language. Excellent work today. You now understand the NLP systems powering language AI. Tomorrow, we explore how computers see. See you then.